Okay, so today we're going to see how do we use the bond energy to calculate the enthalpy change of a reaction. Now you are also provided with a list of the bond energy which is found in your data booklet that you can have access to at any time. And those energy that you can see there, they are very important. They are going to be helpful in calculating the bond energy of a chemical reaction. So the first thing that we want to know if we're going to use the bond energy to calculate the heat of a reaction is what is meant by bond energy. So let us try to see what is a bond energy. So let us first define that term, bond energy. Define bond energy. The bond energy is actually the amount of energy that you need to overcome a 1 mole of gaseous covalent bond. So amount of energy needed. So it is energy needed. That energy is going to be absorbed to overcome 1 mole of a gaseous covalent bond. Gaseous covalent bond. Now, for example, if you take H2, a very basic example, we take H2. H2 exists in the form of H2 gas. This is in the form of H bond H. And the H2 can be broken into 2H. So if ever you are able to break down this bond here, then we are separating the H and the H. The energy that you would need, so the energy that you will absorb in order to overcome this bond, so that it becomes H bond H, so that bond H is broken there. These two H, they are H and H. So they are 2 atoms of H. This energy actually that you are needing there, this energy is referred as bond energy. Now if you take a look at the data booklet, this H bond H is happen to be 436 kilojoule per mole. So what does it say? It says therefore that you would need 436 kilojoule of energy to break 1 mole of H bond H. And when 1 mole of H2 is broken, you are provided with 2 atoms of H. Of course, 2 times 1 mole of the atoms of H. So 436 kilojoule of energy is needed to overcome 1 mole of H2, and you will obtain 2 moles of the atoms of H. If we take a second example, please. A second example, again, in the data booklet, you would have O2, for example. So O2 exists in the gas state. But in O2, you would have it in the form of O double bond O. It doesn't matter how many bonds we have here. What matters is that what would be the energy that we need to overcome those bonds at the same time. Provided that we have a covalent bond here, and provided that we are in the gaseous state, then O2, if we erase the bond that we can see there, if we erase it, we obtained O plus O, which is of course 2O. Of course, all of them, they are in the gaseous state because we're starting with the gaseous state. So it's good to write gas again there. If we look at the data booklet again, we have the energy of O double bond O, and that is 496 kilojoule per mole of O double bond O. So if you need to break down this bond, you would have to provide 496 kilojoule of energy to overcome 1 mole of O double bond O. Now make sure you understand that when you're overcoming 1 mole, you're breaking down both covalent bonds at the same time. You're not breaking down one of them, you're breaking down both of them at the same time. And you are getting at the end 2 moles of oxygen atoms. The double bond has been broken there. So this is what about bond energy is. It is the energy that we need to overcome 1 mole. It's very important to use that term, 1 mole. That is what we are overcoming, what we're breaking. We're breaking 1 mole of, and it has to be in the gaseous state. What happens if it is not in the gaseous state? Then the bond energy is not properly defined, and this energy that we will need there would be a proper value to be used. It would be a proper value when we are in the gaseous state. What now if you are provided with an equation which is like this? So if you are ever provided with, so let's take this one, 2H2 give rise to. So 2H2 is, of course, this is in a gaseous state. This is molecular hydrogen, so it is 2H bond H. And when you overcome them, so one of the H bond H is going to give you 2 atoms of H when this is erased there. But we have 2 of them, so it's going to give 4 atoms of H. So H plus H plus H plus H again. And this is equivalent to 4 atoms of H in the gaseous state. What would be the energy needed there? So the energy would be simply, as we're getting 2 moles of hydrogen gas, and 1 mole of them, as we have seen in the data booklet, 1 mole of hydrogen would need 436 kilojoule of energy. So 2 moles of hydrogen would need 2 times 436 kilojoule of energy. So 2 times 436, that would be the amount of energy needed to overcome 2 moles of hydrogen gas. And in this process, you're forming 4 moles of hydrogen atoms. So everything is balanced to the amount of moles that we have here. So if you were to overcome 2 moles of hydrogen, you would need so much. What about if we want to overcome 3 moles of, let's different color please. So what if I want to overcome 3 moles of oxygen gas? I hope you get the idea now. 3 moles of oxygen gas would give you, now 1 mole is going to give you 2 atoms of O. So we've got 3 moles there, 3 times 2, 6 atoms of O in the gaseous state. How much energy this would need? 1 mole would need 496 kilojoule of energy. So 3 moles would definitely need there 3 times 496 kilojoule of energy. This is the amount of energy needed to overcome 3 moles of oxygen molecule. So this is about bond energy. So let us try to have this back again now, please. I hope that this is understood and there's no difficulty understanding it. The next thing that we're going to do now is to calculate, to explain how the bond energy is related to the reaction itself. So how the bond energy is related to enthalpy change of a reaction. How is it related to? Let's assume that we have a reaction where H2 gas is reacting with Cl2 gas, and this is giving you 2 moles of HCl in the gaseous state. So H2 is this, H bond H gas, and Cl2 is Cl bond Cl gas, and this is giving you there 1 of HCl plus 1 of HCl. And both of them, they are in the gaseous state. So we put a plus there, please. This plus the other one. So in order to overcome bonds, you need energy. In order to break down those bonds, you need to absorb the energy. In order to break down those bonds, you need to absorb energy. These energy are referred as energy needed to break down bonds. So they are bond breaking process. And whenever you are absorbing energy to break down bonds, the reaction is positive. It is endothermic. So endothermic is a term, endothermic. This is a term used to define the amount of energy needed to overcome covalent bonds or to overcome bonds. Or it is a reaction where heat energy, so heat energy is absorbed from the surrounding. This is an endothermic process. On the other hand, if you look at the product there, the excess energy would now be liberated. When the bonds had been formed, the excess energy is liberated. This reaction liberates energy, so it is an exothermic process. Exothermic process. And this energy is released, so we say that it is a negative process. It releases energy. Now, the heat of that reaction, the heat of what we want to calculate, the heat of the reaction there, would be the difference between the amount of energy absorbed and the amount of energy liberated. Let's say that we are absorbing more energy that we are releasing. So if we absorbed more energy, let's assume that we are absorbing 10 units of energy, but we're releasing only 5 units of energy. So what would happen is that we're releasing, I would take another value because it's going to be the same. We're releasing 6 units of energy. That would be better. So we are absorbing 10 units of energy. We are releasing 6 units of energy. This is energy released. The thing is, as if the net change is that we have taken 4 units of energy. So taken 4 units of energy is going to be endothermic by 4. As you can see, it's going to be endothermic by 4 because this is the amount of energy intake, the energy needed to overcome those bonds, and this is the amount of energy released when those bonds have been breaking. And the difference between them, the net change, is as if that we have been needing all 4 units of energy. These 4 units of energy has been used up in the process. So it is going to be a reaction which is said to be endothermic by 4 units. On the other hand, let's try to see another one now. Let's assume that this time we're taking again, 4 units again. So we're taking, we're taking 12 units of energy. So this time the reaction is absorbing 12 units of energy. So it is endothermic by 12 units. 12 units of energy is needed to overcome those bonds. But the reaction releases 18 units of energy. The thing is that we are absorbing 12 units of energy to break down the bonds, and when the reaction is completed, the reaction is exothermic by 18 units of energy. So as a change there, it is as if we have released there 6 units of energy. So this reaction is going to be exothermic by 6 units of energy. So we are releasing energy during the process. The whole enthalpy change would be 6 units of energy. So in this way, we can use these bond energy to calculate the amount of energy released in a process. This is the process, H2 converting into H2 plus Cl2 converting into HCl. This reaction is going to be exothermic by 6 units of energy. This is the basic, the foundation of what we're going to use in a while to calculate the heat of a chemical process using bond energy values. Of course, there are some limitations behind them. We'll see the limitations in other videos that will come afterward. And there are also this controversy that you will always look about, that you would always be seeing or be trying to understand that this is energy created, this is energy being destroyed. No, this is not the case. We'll try to explain them afterward. This is a short way by which we can obtain the heat of a reaction. We're not creating energy there. This is always a question that many students ask me. If you're using 12 units and then you're releasing 18 units, it is as if you have been creating 6 units of energy. And we all know about the conservation of energy that says that energy can neither be created nor be destroyed, but can change one form to the other form. So there are hidden things that I have not explained here, of course, that we can get them back in a new video. There are many ways of doing it. There are many ways of understanding it. We can get back to them afterward. But for the time being, this is one way. This is one way by which we can work it up and we can obtain a value at the end. This value is used and in your exam papers, and you can have correct answers easily. So you forget about this conservation for the time being and thinking about it, that you can think behind that we can always explain them to you afterward in new videos. For the time being, you take them like this and you would see that this is very easy to understand and very easy to calculate. There's no big difficulties behind it. So this is how the bond energy is related to the enthalpy change of a reaction. So what we can say at the end for this part here is that every time bond breaking is going to be an endothermic process, while bond formation, as you can see, we're forming new bonds there, this is always going to be an exothermic process. This is a rule that you can use in most of the calculation. You can use it every time. It is very helpful. So how do we calculate now? This time we're going to calculate the energy of some molecules. So let us take another color now, please. So we're calculating energy of molecules. molecules, energy of molecules. Now each molecule would have a certain amount of energy. If I take, for example, hydrogen that I have said in a while, H bond H, there is a certain amount of energy which is locked inside this bond. These are usually referred as the potential energy of molecule. So potential energy of molecules. So all molecules, they have a potential of energy. They've got energy inside them. This is why, for example, when you're eating food, for example, you're taking glucose, you're getting energy from that glucose. Because the glucose is rich in energy, we've got a potential of energy inside that glucose. So if you, for example, if you eat a compound with much more potential of energy, you're supposed to get much more of that energy, provided that these energy are made available to you. That is, it is broken down in your body and the energy is released during respiration. So H2, it has a potential of energy. Inside the H2, we've got about 436 joule of energy, kilojoule of energy for 1 mole of hydrogen gas. So 1 mole of it, we have so much of energy. If somebody asks you to please calculate the energy of methane, so how do we do it? Energy of methane. Now methane is drawn like this, CH4, and don't forget that methane is also a gas. So methane is CH4 gas. And in methane, what we can see is that we've got 4 CH, 4 of them, and 1 CH, if you look in the data booklet. So 1 C bond H, where it is, 1 C bond H. Here, at the very beginning. So 1 C bond H is going to be 410 kilojoule of energy. So 1 of it is going to be 410. 4 of it is going to be 4 times 410. You see, this is a very quick way by which we can obtain the potential energy of methane, the energy which is locked inside methane. And if we calculate this, it is 1640 kilojoule for 1 mole of methane. So every time you're breaking 1 mole of methane, you would need 1640 kilojoule of energy. How much energy now is found in O double bond O? So directly from the data booklet. There's no need to calculate it. It is found in the data booklet because we don't have any calculation to make there. O double bond O in the data booklet. This is 496 kilojoule. So that is going to be 496 kilojoule of energy. How much energy is found in the carbon dioxide? Let us take this one now. So this is, let's divide this. These are 2 calculations. This is for the methane. This is for the oxygen. We don't run out of space, otherwise we're going to run out of space if we continue like this. So let us calculate now for carbon dioxide. So carbon dioxide, first you need to draw it in order to see how many bonds we have in it. So it's important to know how to draw the structures. Carbon dioxide, if you can recall, it's a linear compound with double bonds there. Carbon dioxide consists of C double bond O. So there's 2 C double bond O in 1 carbon dioxide. And what we only have to do is to look for the energy of C double bond O in the data booklet. And this is taken to be 740 kilojoule per moles, as you can see there. So 742 times 740. This will give you 1480. That is the amount of energy, kilojoule of energy that you need to overcome 1 mole of carbon dioxide. Remember, it is 1 mole of carbon dioxide. So if ever we're getting much more moles of carbon dioxide, this will be 1480 times that amount of carbon dioxide, that amount of moles of carbon dioxide. This we're calculating for 1 mole. So we calculate for another one. Let us calculate for something which is known to each and every one of us. We calculate for water. How much energy is found in water? So water is H2O. Remember, when we are calculating it, we're making sure that we calculate in the gaseous state. Now, if you're saying that water is in a liquid state, of course, this is one limitation that makes our calculation slightly different from it was supposed to be. So water in the gaseous state we're calculating. And in the gaseous state, water is OH. 2 like this, and it's a bent compound. If you want to go in more details, we've got 2 lone pairs there. It has a bent shape. The angle is in the region of 104 units there. So water, there's in water 2 times O bond H. And we look at O bond H in data booklet, how much it is. So this is going to be 2 times O bond H. Where is the O bond H now? O bond H. Here it is, 460 460 kilojoule per mole. So what it would be, 2 times 460 kilojoule, and this will be evaluated as 920 kilojoule of energy to overcome 1 mole of gaseous water. Remember, the gaseous water is very important. It has to be in the gaseous state. So 920 units. Now we're going to use those values. As you can see, bond energies, we have a lot of energy in those molecules. In the methane, we've got about 1640. In the oxygen, 496 kilojoule from 1 mole of oxygen. For the carbon dioxide, 1480 for each mole, kilojoule of energy for each mole of carbon dioxide. And for the water, 920 kilojoule for each mole of water, of gaseous water. What if I want to calculate now? Oh, we're running out of space, so we can get rid of those now, please. So let us get rid of them. That takes a bit of time. So let me do it quickly, like this. Is it okay? Yes, it goes away. So we are now going in a while to calculate the energy of a chemical process based on what we have seen. And the chemical process is that I'm going to take a chemical process which is very much similar to what we have evaluated, that is the methane and the oxygen. Let us take it quickly, please. Yes. Here it is. So now we can start working on it. We're running out of space. That's why we're doing it. Okay, so we want now to calculate the enthalpy change of that reaction. Which reaction? So we've got CH4, which is a gas, and we're burning it in oxygen, O2, which is also a gas. That gives us there carbon dioxide, which is also a gas, and water, which is also, for our case here, a gas. For our example, a gas. First, you need to know is to balance the equation. It's very, very, very important to balance the equation. If you don't balance it, then we don't know the number of moles that we've been using there, what we've been producing over there. And remember that those number of moles, they are strictly related to the amount of energy. So 1 mole is going to be 1640. If it is more than 1 mole, it's going to be more than 1640. If it is less than 1 mole, it's going to be less than 6040 kilojoules. So we have to balance our equation. And if we balance it, we've got there 1 carbon and 4 H there. So 2 of them here. And we've got 2 of the water, 2 of the oxygen. I think the equation is balanced. 2 and 2, that amounts to 4. Good, now that our equation is balanced, we can now start drawing it. So it's important also to draw so that we can see how many bonds are there. I'm not deliberately putting the H there, you can put them, plus 2 moles of oxygen gas, and that should be in the gas state. So gas and gas. That should be in the gas state. That gives us carbon dioxide. So this is a linear compound in the gas state. And 2 moles of water. So 2 moles of water. Water is a bent molecule, remember. So 2 moles of water like this. Now, fortunately for us, we have already calculated all these potential energies of those molecules. What we do now, we're putting them back again below. So let's put them back again below. So for methane is going to be 1640. So that is 1640 amount of energy which is locked inside methane. For the oxygen, it's going to be 496. So that is 496, but of course, the 496 would have to be multiplied by 2 in order to obtain the energy locked in 2 moles of oxygen. Remember, we're not using 1 mole, we'll be using 2 moles. So you can see the importance of balancing that equation. If you don't balance the equation, this number 2 will not appear there. And for the product there, we have 1 mole of carbon dioxide, and we have the value, 1 mole of carbon dioxide is 1480. So 1 mole of carbon dioxide, 1480. And we are producing 2 moles of, so 2 times, and the energy locked, the potential energy locked inside water is 920. So that is 2 times 920 kilojoule of energy. Now what do? We apply what we have said before. We apply the concept of this. That is, on the reactant side, we need energy. We need to absorb the energy, bond breaking. On the product side, we need to form the energy, bond formation. This is endothermic, and this is exothermic. And the energy change is going to be the difference between them, between the amount of energy absorbed and the amount of energy released. This is exactly the same. So let's apply it and let's obtain the answer. So if we apply, we need so much of energy to break the bonds. So you will take 1640 plus 2 times 496. You sum this up. This is like this. You sum this up. This is going to be a certain value. Then this is the energy absorbed. We put a plus there. And we sum up this one also. 1480 plus 2 times 920. You sum this up. So if we sum up this, we obtain a value there. And this value is negative so much. And then we can calculate the difference between those two values. Now, I should leave this on you to calculate, and you should be able to calculate them, and the difference between them would give you the energy. The energy would be, of course, in kilojoules. A very simple process that you can do. In the next video, of course, I'll give you the answer for this. I'll not give you the answer right now. You calculate it and you should be getting the answer. If you can post the answer also, that would be very nice, and the others can see the answer. I have done most of everything for you. So this is positive so much. This is negative so much. Then what we do, we take the sum between those two. We take the sum. This is going to be energy absorbed. This is going to be energy released. And this calculated value is going to be the enthalpy change of that reaction. So we have calculated and we have been able to calculate the enthalpy change of that reaction using bond energy values. Questions should not be more difficult than this in exam papers. You would see them a couple of times, and they are usually seen in paper 2. So if you have any queries about it, please feel free to ask. Thank you.